So I actually want to start with sort of an apology, right? So if you look at the Dynamic Walking 2009 website, there was this error, I think. It said somewhere in the middle there, it said dynamic walking approach puts less emphasis on a few things, and motion planning was on that list. And I think this was a big mistake, right? And actually, as your webmaster for this year, I can guarantee that this error has been corrected. And you won't see that in the list, or at least it'll be modified appropriately. And what I want to do today, actually, is try to convince you that motion planning is really central to the way we should be thinking about dynamic walking. And I hope maybe it even, instead of being on the not list, maybe it makes it to the things we do talk about every meeting. We'll see. But I want to try to make that argument to you by using the model we all know and love and we've been talking about a lot this week. So your standard compass gate model, which, as we know, has a stable limit cycle down the ramp with the standard assumptions. I have only torque at the hip, so no torque at the toe. Okay. Let me tell you about why you need motion planning, maybe, by just trying to articulate what I care about from the control system, my goals for control. So the first thing we should have, I guess, is this is the nominal limit cycle of the compass gate walker. We've seen it a couple times now. The first thing I'd like to do is make this nominal gate very, very robust to initial conditions. So right from Ambarish's paper many years ago, he cartooned the limit cycle of the compass gate, and we all know that the passive compass gate is relatively fragile. It can only recover from small initial conditions. And we've got a lot of good control approaches now for making that bigger, but I really want to fill up the entire space as much as I can with the control system. I want to have it as robust as the system is capable of being. A second goal for the control system would be to walk on rough terrain. And this is a picture of some work that Fumiya Aida had done in our lab. And Katie Bill was also working on walking on rough terrain. And that certainly motivates motion planning. And my third goal for these walkers is efficiency, but really it's a distant third. I think that my answer to efficiency is maybe about what Jesse said too, that we should do everything, we get the stability first, we'll use trajectory optimization to get the most efficient gate we want to stabilize, but I think first you have to be stable and then we'll worry about efficiency. Okay, so why are those challenges hard? And we've heard it in a couple different varieties. Here's my answer. So the reason I think walking is hard to control, it's not hard to stabilize, Andy, but it's hard to control very, very well because of the dynamic constraints. First of all, we've been talking about underactuation, which means you can't follow arbitrary trajectories, but maybe even a more dramatic constraint are the power limits at the actuators, which manifest themselves as either torque or speed limits or both. And those can really, really dominate. Okay, so for instance, on the Little Dog robot built by Boston Dynamics, we've been thinking about trying to make Little Dog bound. And in this is a high-speed video slowed down. In this bounding motion for Little Dog, at every instant in time, almost every motor is absolutely speed saturated. And Chris could tell you all about it too. So, and that's just, I think that's just a real issue. I think, Big Dog is instead torque saturated, but every walking robot has to carry its actuators as some limits in power, and eventually these saturations, when we're trying to move really fast, are going to come into play. And there's other dynamic constraints, right? Limits on ground reaction forces from the friction cone. All these things are fairly complicated constraints to reason about in the control system. Okay, so I look around at all the solutions from the robotics community, from the controls community, and tried to make a list of what works well. So trajectory optimization works well. We had a nice tutorial on that yesterday. It's a very powerful set of tools. As you saw, it can handle constraints very naturally. You can just write down a series of constraints. So that's one tool that could potentially deal with the complexity. Stabilization of these trajectories works well now, thanks to Jesse, thanks to Anton. Local orbital stabilization can work very, very well. It's more difficult maybe to naturally handle the constraints, but if you have a local linearization, you could do, for instance, model predictive control or something like that, but it's more difficult to say rigorous things about the feedback that handles those constraints. But there's another set of tools that we haven't been talking about much yet, which I think should be part of this recipe. Okay, so one of those is global feasible motion planning, which can also handle constraints, and I'll tell you what that is and how it relates to the others. And then there's another set of tools which is about estimating regions of attraction. And again, we can handle the constraints with those. And really, my solution to the walking problem right now is to take these things that work well and try to put them together into a soup that can solve our hard problems, I think. So I want to tell you about what's going to smack of computational and computer science, I guess, but a very computational approach to designing high-performance, provably stable controllers. Okay, so let's talk a little bit about what trajectory optimization does and what it can't do, right? So we saw lots of cases of it working in the tutorial, but if I were to, for instance, ask even a simple car or something like this to drive from this initial condition subject to a constraint that it has to get to this goal, and it was in a bug trap, right? Then the local trajectory optimizer is going to try to smack itself against the wall. It might walk around a little bit trying to satisfy the constraint, but because it's a local method, ultimately using gradients, it's never going to find a solution that's going to walk itself all the way around outside this little tunnel and get to the goal. Okay, so there are limitations in the completeness of trajectory optimization. But there are tools that can solve this problem. So rapidly exploring randomized trees, and I'll tell you how they work, but this visually will tell you how they work. They're more exhaustive computational approaches that try to fill a space with feasible trajectories and will eventually find their way outside of even a bug trap and make itself to a goal. And these algorithms, unlike the trajectory optimization, they throw out optimality at first blush. People have been trying to put optimality back in. But they have strong notions of completeness, saying that if it's possible to get from some initial condition to the goal, then this will actually eventually find that path, or at least with probability 1 as time goes to infinity. Yeah. Okay, so this is a good set of tools to add to the library. Now this is a pretty boring, this is not much dynamics in this example, but let me show you that it does work with dynamics too. Okay, so here's the basic algorithm. You can understand it very quickly. So if I have some initial set of solutions, each of these nodes represents a feasible configuration of the robot. Each of the edges represents a feasible trajectory of the robot. If I have some set of solutions that I've already considered, and I want to start expanding, continue to expand to try to find my way to the goal, then the algorithm's pretty simple. I'm just going to pick a new point at random somewhere in the state space, try to find, by some metric of distance, the closest node on the tree, and then try to extend my tree a little bit in the direction of that previous node. Very, very easy to describe. And this algorithm does exactly what I showed you on that last slide. It'll start quickly populating the space with these fractal-looking trajectories, and will find its way eventually through nooks and crannies and get you to the goal. Okay? And the immediate knee-jerk reaction that I hope you have is that there's no way that's going to work in high dimensions. And the answer I can give you is only anecdotal, but it surprisingly works well in very high dimensions. So James Kuffner was doing beautiful work. This was a 32-dimensional simulation of a humanoid reaching under severe constraints with the ZMP constraint, trying to reach under, not hit the chair, and pick up a flashlight. And he's got a very impressive body of work showing that these methods can really do surprisingly well, especially with heuristics, but even some of the vanilla algorithms work surprisingly well in very high dimensional spaces. Okay, so I think they should be on our radar at this meeting.
Can you say why?
Yeah?
Can you say why they don't suffer from the curse of dimensionality?
Oh, for completeness, they absolutely do suffer from the curse of dimensionality. The argument I can give you is this Voronoi bias, that they efficiently fill a space very quickly, right, because of the Voronoi bias. And even in high dimensions, they're biased to go to the big empty spaces, and heuristically that scales, right?
How important is heuristically?
Oh, sorry. Maybe I should say anecdotally that scale. I mean, so far people that have tried have been very happy with it. They're trying to pull proteins with it. They're doing very high dimensional things, right?
I guess what I'm asking is the same thing as Andy said. Is it a sort of a unknown known? Could it be that the heuristics are what makes it work and not the method?
So I think initially that might have been true, but I think that just by the number of people that have been able to repeat the success, I think that many of the knowns are known, probably, yeah. Okay, so I gave you a pretty kinematic example first. Let me give you a more dynamic one, although a very simple one. Imagine now a simple pendulum with a torque at the base, and we just want to take this simple pendulum and swing up and balance at the top. But we're going to impose torque limits, for instance. Now this actually you could probably do with trajectory optimization. With a good initial condition, your trajectory optimizer might find a very good path straight to the top. But let's say we want to do it with a more complete method. So we can take that rapidly exploring tree, and grow trees. In the good cases, you tend to grow them backwards from the goal as well as forwards from the goal. This is the state space of the pendulum, theta versus theta dot. This is the down. This is the top configuration wrapped around because it lives on the torus. Okay, and these trees will grow out in random directions. And because every edge of the tree represents a feasible trajectory, it naturally starts expressing the dynamics of the system, right? So this is the eyeball that you all know and love from a simple pendulum. This is the natural dynamics of the system expressed out of a very random algorithm, okay? And they'll eventually connect up and find you a path, if it exists. Okay, but actually the initial algorithms as proposed don't work that well. And in fact, if you spend enough time doing it, you look at it and you see every time you pick a random point, it kind of picks the wrong node to expand from. You start feeling it's pretty inefficient. There's a lot of things that could be better about it. So there's been a handful of work we've done and other groups have been doing to try to make them work better for systems with dynamics living in state spaces, which have natural tendencies to, for instance, go clockwise around the phase portrait. And there's a number of heuristics that you can do. So you can try to improve the way that you sample random points. You can try to improve the notion of which point is closest. You can try to extend in a way that's more natural. And we've been exploring all of these. Let me tell you quickly about two of them. So Alec, who's in the audience here, has got this very clever trick for changing the sampling distribution. It's very inexpensive to implement, and effectively the problem with growing these things in state space is you end up trying to grow in places where you just can't get. So for instance, you just keep asking it to get to the top and it's only got enough energy to live down near the bottom, and it's annoying. So what you end up doing is, what Alec has done is come up with a way to sample only from the green regions in this plot, which are a local estimate of places where the pendulum can move in a few samples. And it's a moving target, but we come up with these sort of moving sampling distributions which guide the expression of these dynamics so that they're considerably more efficient for dynamical systems.
How do they choose the green tree?
So actually he grows two trees. He grows the nominal tree that you're planning with, and then he also, every time he expands, he has some local estimate of the reachability for that node. And if you're closest to the boundaries of your reachable set, instead of closest to the existing tree, then you're in this green Voronoi region, which means you have room to grow. Yeah. And
This is the growing oscillations you're showing there.
it is it's for the pendulum case.
It's being pumped.
Yeah.
And why is it trying to pump up instead of pump down? It's just trying to supply new regions that hasn't been near before?
That's right. It's biased. There's much higher probability of sampling from a place that's not near the origin. So it has this natural tendency to fill the space. And then actually after that has happened, it's got this nice property that random samples are just as likely to express the ones that are close. So these things sort of fill the space quickly and then fill in the details later. If you watch them enough, it has that behavior. And little tricks like this can make a big difference to the performance of the algorithm. Okay, so Alec's version of the simple pendulum plotted versus just a standard RRT. This one cruises right up and finds a goal. This one's still just getting started. And there's a handful of tricks you need to do. All I mean to really say is that with a little bit of tricks, you can make these things work very well with dynamical systems. It works. Alec can also solve these bug trap problems in a blink of an eye in a few trajectories using similar kind of heuristics. Okay, so let me show you a harder example. So we can do this, for instance, on little dog. So we take the little dog model. We spent also a long time doing system identification for little dog, but we came up with a pretty good model. I'm not sure if we'd say we'd like it as much as yours, but we came up with quite a good model. It's a planar model, so we just ignore the out-of-plane dynamics, a 5-link model. We model the ground reaction forces very carefully and the dominant effects of the saturations at the joints and the inertia of the motors, reflected inertia of the motors. Okay, and then we plan in this high-dimensional space. It's a total of 18-dimensional space that we're planning in. There's some primitives that we use, so we plan half bounds at a time. And we can now take little dog and very quickly plan pretty complicated trajectories over surprisingly not convex terrain. So this is just a system. It says you've got a robot. It's described by these following dynamics. It's got these kinematic constraints. Initial conditions here. Final condition is here. go to it, and it fills up the space and comes up with a trajectory that gets you over the obstacles.
Does the actuator limitations in the simulation match the real world?
Oh yeah, we spend more time on that than anything. That absolutely dominates. And actually, we do delays and simulation and everything like that too. Okay, so another key idea is to improve the way we do the extend operation. So for instance, everything you learned in the trajectory optimization the other day, nowadays, every time we do a little extension, instead of growing some epsilon towards your goal, we actually do a trajectory optimization during every extend operation. That makes a huge difference. Okay, but the take-home message is really that these randomized algorithms can find solutions in pretty complicated dynamic problems. Okay, so once we find this solution now, we do what Jesse does and what Anton does to stabilize the motion plans with linear feedback. And here's how that looks on my slide here. So if we have our initial time-varying, our initial nonlinear system, we're going to do a time-varying linearization along the nominal trajectory. We'll design a time-varying linear feedback, for instance, using the linear quadratic regulators. That's not necessarily essential. And it really does make a huge, huge difference stabilizing only the transverse coordinates or stabilizing in phase instead of stabilizing in time. And the practical way you see that is just when you start integrating back the solutions for this, the controllability is just, the numerics of the problem are very, very bad. And you take out one dimension and suddenly the numerical conditioning is very, very good and the controllability and the system works much, much better. Okay, so Michael's been showing you can do the transverse linearization even on these complicated models on Little Dog. Now you might be able to guess this is the one that wasn't transversely stabilized. The green one I think was the original and the blue one was the stabilized one. Okay, so in pretty complicated regimes with that one, by the way, the dog is getting perturbed. There's an adversarial perturbation. Every time the foot hits the ground, someone's trying to throw it back up with some pretty big perturbations, and there's delay in the model and everything too. And it's still very robust. Much more robust than our initial attempts. Our use of transverse linearization is just a little bit different than what Anton said. We don't typically use the trick of virtual holonomic constraints yielding analytical transversal coordinates. We do transversal coordinates designed numerically, and we actually spend a lot of time optimizing our choice of transverse sections, but that's maybe a detail. Actually, Anton made some nice points about how if you have it analytically, that can help with the robustness analysis. We don't do that yet. Okay, the third tool, I don't know, how many tools have I had? Fourth tool maybe is estimating the regions of attraction. Okay, so, and that was prompted nicely by Bobby and other speakers. It's really, really nice tool to be able to efficiently estimate the regions of attraction of these systems. So let me do it on the pendulum example again. So the simple pendulum, if I were to swing up and stabilize this at the top, let's say I just even put it at the top configuration, which is pi 0 on is that 0 to you? It looks, maybe my perspective's wrong. That should be at 0 though, okay, yeah. So pi 0, so I stabilize the system around the upright. I'll just do it with an LQR, a linear feedback design. Okay, but now I want to estimate the region of attraction of that linear controller. So you know from sort of intro controls that the linear controller works great up here. If you start moving too far away, the sine theta term in the pendulum means that the linear control stops working. Okay, so at some point it fails. Actually, the region that it fails is not symmetric because it's better to be over here with a velocity going this way than over here with a velocity going this way. And you get these sort of, it's not a perfect ellipse, but we are going to make our best ellipsoidal approximation of the initial conditions, which when running a linear controller on this nonlinear system, make it up to the goal, okay? And the surprising thing is that we can get that estimate very efficiently now. And here's how that works. So we're going to estimate regions of attraction for linear feedback. So given a differentiable plant, again, we're going to linearize around the operating point. We're going to use our LQR design to get a linear feedback, again. But LQR design, of course, also gives you X transpose SX, which is the cost to go for the linear feedback. So if you were running the linear feedback on the linear system, this function is always decreasing. The cost to go will always go down. Okay, which makes it a valid Lyapunov function for the linear system. It's a proof of stability for the linear system. And what we're going to do now is to estimate the region of attraction is we're going to ask for what region of state space is this Lyapunov function still a valid Lyapunov function for the nonlinear system. Okay, so we're going to look for the largest level set of this quadratic function, parameterized by rho, for which all x inside that rho have the property that we're going to go down the bowl. And I'll show this visually in just a second. Okay, so this is a bowl around the origin in that ellipse. We're going to find the biggest level set for which this Lyapunov function is a valid one for the nonlinear system. And it turns out it's surprisingly efficient to do this exactly. It can be formulated with an affine objective over the convex cone of positive definite matrices using sums of squares optimization. I decided to yank the slides that get really into the details of sums of squares, but basically this means that you can formulate a semi-definite program that will exactly tell you if the solution without any local minima using very good convex optimization tools. Yeah.
You're not showing saturation there, but you do it in the optimization.
Yeah, that's right. So we add saturations also. Yeah. And the cool thing is that it's an exact verification. So you'd be tempted to say that in order to estimate the region of attraction, you'd need to simulate the system from a bunch of places or something like that. We're not doing any simulation, no sampling. It's an exact algebraic evaluation of these dynamics on this function and saying that that region exactly is stable.
The Taylor expansion isn't free.
So do I say Taylor expansion here? No, so we started doing Taylor expansions. We've gotten much more mature about it, and I'll say that. So we don't actually do the Taylor expansions. Yeah, or we can, sometimes we do, but we don't have to, so. Okay, so in our group, we've been working hard on these sums of squares methods now for the last year. I gave a bit of this talk last year, and last year it was, the title was Wild Speculation, and there were a lot of asterisks and question marks in the talk. And this is now just many of the same slides, but where the answers have been filled in. So in particular, Mark and Ian have been fantastic working on this stuff. Mark in particular was working on it till late last night. I hope he's awake again and so I can thank him. So we've been extending the sums of squares region of attraction estimate to doing stabilizing trajectories. I'll show you that in a second. We're doing exact verification despite inevitable errors in the numerical integration. Just that we're doing this right, I think. We've got good tools for doing it with trigonometrics exactly without doing the Taylor expansion, okay? Which nobody in controls would be surprised about, but the tools just weren't really there. And Ian's going to tell you on Saturday that we can do it exactly to do the region of verification for limit cycles with impacts. Okay, so here's how it plays out. So being able to estimate the regions of attraction, in my view, changes everything. Suddenly we have a really, really nice tool for motion planning. Okay, so now let's take the simple pendulum. We're going to start it in the downward configuration. We've already know how to stabilize it at the top. We designed a linear feedback. We estimated its region of attraction. Now we're going to do trajectory optimization to figure out a solution to get me from the bottom to the top and swinging up and balancing. But I'm going to now do two extra steps. I'm going to stabilize that trajectory with a linear feedback, time varying or transversal linear feedback. And then I'm going to compute this invariant set around this trajectory. It's an invariant set in the extended state space, to be careful. And it's a tube that says any initial conditions which start in this tube are going to stay in this tube, and they're going to find a way to the outlet of the tube. And as long as they find their way in the outlet of this tube, and the outlet of that tube is the inlet of this tube, then I've got a proof that I'm going to get to the top. And you can think of it like the funnels that we've been seeing a lot. Okay, so each of these tubes that we're verifying are exactly these funnels that we've been thinking about in controls for a long time, and now we have good tools for calculating them. And as long as I have my funnels leading into other funnels, then I have cascaded plans which get me to the goal. Okay, with exact proofs of stability if we care about that. And these funnels give you a really, really nice way to do fast planning online because suddenly you can throw around funnels, these abstract objects which are just funnels, instead of having to do real-time motion planning with just trajectories, for instance. Okay, so yeah, this is my nice 3D animation of the funnel. Yeah. Okay, so the funnels have been around for a long time. They're credited to various people. I learned about them honestly first from Dan and Al's paper, which I think is fantastic. They cited Mason, and Mason says, Mason says I shouldn't credit him at all. Every time I see him, he says, I don't know why you give me credit for the funnel idea. First of all, everybody knows about funnels. Second of all, I don't think I even came up with it. And he actually says, I think I probably learned about it from Mark. So this is sort of citation in progress. But funnels are a good idea, and everybody likes them. So, okay, so the cool thing is that really gives you a really good tool for motion planning. So here's my rapidly exploring tree for feedback motion planning. I'm going to pick a point at random in state space. I'm going to design a trajectory that gets me back to the goal. And then I'll stabilize it and compute the funnel. Okay? Now I'll pick a new point at state space. If it was already inside the funnel, I'm done. No need to add it. If it's outside, I just need to design a trajectory with the final value constraint just says it has to land somewhere on the tree, somewhere on the existing tree. And I fill that in and stabilize that. And what happens is after just a handful of trajectories, you can fill the space with motion plans that are guaranteed that every initial condition is somehow found its way into the funnel. Okay? And the cool thing is it only takes a handful of these trajectories to fill the space, at least for low-dimensional systems. And not particularly impressive, but we can swing up a pendulum and balance it. Okay? The algorithm taking from the rapidly exploring tree kind of literature has strong properties of coverage. So now we can say it probabilistically covers the controllable space with stabilizing controller. So what does that mean? So that means if there was some region of state space which wasn't inside the funnel to begin with, we'll eventually sample it. And if it's possible to get it back to the tree, we'll eventually connect it back to the tree and cover it with a funnel. So that means any initial condition that can reach the goal will eventually be inside the basin of attraction of our controller. Okay, that's pretty cool for even complicated nonlinear systems with saturations and constraints. Okay, and here's John cooked up this nice example, which is where he designed a system that was, because of input limits, had a known region where it could never possibly recover from things beyond this region of state space. The goal was here. He sampled over this cyan region, and what the algorithm did, because we're using ellipsoidal regions, it just started populating the wall of this region closer and closer until it could fill every possible region to cover the space and get it to the goal. Obviously, if we used non-ellipsoidal regions, we could have maybe done it more efficiently, but this just shows that that's what it does. If there's some gap there, it'll eventually grab it and add it to the tree. Okay, so it was sort of hard to implement. That's actually, I think the downfall is that it was pretty hard to get all this stuff working. So we had to do a lot of work with numerical optimization and conditioning problems, and we use now Sasha Magretsky's tools for the sums of squares. Lots of numerical massaging, trajectory optimization methods, and we do robust verification inside this, sometimes in the control design, but mostly just in the verification. So we're trying to release the version of the toolbox for MATLAB, so if you guys want to try it. Now, because it uses all these tools, it's been a little bit of a pain handing it to people. But if you're willing to try, then I'm willing to try to help you install the tools and get it working. Just send me an email. Okay, so now I've been thinking for a long time about all these underactuated systems and how to design controllers for it. And I don't want to say that they're solved. There's lots of things that we can do. But any of these systems of this complexity now, we can just we just hand it to the same algorithm, bang out controllers that will fill the space. Every initial condition that can get to the goal will get to the goal with some proof of stability. Now, when I first talked to Mark Spong about this, he pointed out immediately and correctly that things like energy shaping on this are very robust to parameter errors and things like that. And so that's absolutely true. And I think the work that needs to be, so what it would manifest, if I design a linear controller in some metric space that was not robust to parameters, then I'll get a small funnel, right? And so if I use the right representations, I'll get a big funnel. And energy shaping is almost certainly the right representation for these guys. So there's work to be done. It's not to say they're particularly efficient. It couldn't be more efficient. But we can, for the systems of this complexity, bang out controllers that are as good as they need to be, I guess. This is just an example on the cart pole. The light's going to turn on as soon as the controller turns on. There's constraints on the travel, which make it a little bit tougher. They're all handled exactly in the algorithm, and we can now, get back to the top no matter what you do to the pendulum.
How many regions for that example, say?
42 trajectories, I believe. Yeah.
So it's pre-calculated based on the known dynamics?
Yeah, we model the system. I'll talk a little bit about the dependence of the model at the end. Yeah.
So is the trajectory trying to get to a point that you pick in advance, or are you just picking at random?
So we label a goal, which is in the middle upright for that cart goal, and everything's trying to get back to that.
But when you just do when you grow one step in the tree,
You try to grow back to the existing tree. It's allowed to walk, the final value constraint is to the manifold, which is the tree, and you're allowed to walk along the tree.
okay.
But you're in my lab, you can ask me later. Yeah. Okay, so now we can do it for the compass case. We can do it for limit cycles with impacts. And Ian's, it's a nice combination of what Anton was telling you and all these SumsofSquares tools, and the story I think is beautiful, and Ian is fantastic. So he's going to tell you about that on Saturday. But this was really, really exciting to me to be able to do it for exactly for limit cycles. So. A lot of times our proofs of stability in walking have been limited to when we can integrate across the entire Poincare map, and now we can do regional statements of stability without having to integrate exactly. In practice, we often, to be faster, we don't do the exact solutions. We end up doing sampling along the trajectory instead of exactness along the trajectory, but we have all the things lined up to do the exact thing if we really needed to.
How do you do LQR with non-smooth dynamics?
So we do it on the transverse coordinates to get the orbital stability, and then it's just a jump Riccati equation through the discontinuity. Yeah. Okay, so then the way I think we should do walking is we should do this, and this is the thing that I think we've got a lot of good tools to do, is to stabilize the nominal limit cycle, and then we just do a little bit more. Now that we've computed this region of attraction, we can start adding. We just grab a new initial condition that's outside the region of attraction, do trajectory optimization to design a motion that gets you back to the nominal limit cycle, stabilize that, compute its funnel, add it to the tree. And the claim is that after you grab a handful of these recovery motions, then you'll quickly fill the available space so that initial conditions where the compass gate can get back to the goal, it will get back to the goal. Okay, so, and the effect is, this is the trajectory library, the thing that Chris has been saying forever, and we now are in the same camp of believing in these. So maybe you just need to have a handful of sort of recovery motions. Maybe me as a walker, I just need to have a handful of recovery motions, and I can use those in a lot of situations. The situations I can use them for are computed by these funnels, and just fill the space with a handful of motions. And I'll fill as big of space as I can. Okay, so like I told you in the intro, we built this biped to try to show that we could do it in real life. And it worked for the first time, like it walked for the first time on Wednesday. Zach's a fantastic designer, and he's going to bring it over for a couple times so you can see it. But it's a work in progress, and so soon you'll see the LQR trees working on this. Okay, and it also works for other systems. I just want to say quickly, so I really like the control ideas, the general dynamics ideas that aren't just for walking. Walking's fun, I love walking, but it should be bigger than that, right? So it's cool to say that the same algorithms work for other systems. The other one we've been thinking a lot is these perching aircraft, which are difficult because they're in a complicated fluid regime. If you try to land on a perch like a bird, then you go into this deep stall configuration where the dynamics are very complicated, the nonlinear dynamics dominate, the saturations dominate. So it's really hard for a lot of the same reasons as walking, except for impacts. Well, I guess we impact the perch, but we ignore that, yeah. And the same sort of algorithms can now make us go up and build these planes which can stall their wings and land on a perch. We did this initially with dynamic programming solutions, but we're doing it much more successfully now with basically 100% success rate using trajectory stabilization and a form of the LQR trees. And it's a robust phenomenon, so this is just another trajectory of it landing on the perch. And we collaborating with Mark Kokoski to put some spines on there. We can land on a wall. The Air Force wants to land on a power line. It's been a good thing to think about, yeah. And the way it works is exactly like the story I said for walking. So we design a nominal trajectory from an initial condition. We compute the stabilizing controller, compute its region of attraction, or estimate the region of attraction, and then try to fill the space with trajectories that get us back to the goal, right? So we can be very robust to a lot of different initial conditions. Okay, so it's a very model. Oh, sure, yeah.
Does your model change as it approaches?
We did a system identification procedure. Rick did a system identification procedure where he shot it about 200 times and tried to comb the set of states that it could possibly enter. Built a model once, which was a surprisingly simple model, and then we've used that for all the experiments. So far we haven't gone. We haven't gone to the point where we needed a new model because of the new trajectory. But we can add in, we haven't done it for the perching, but we can add in, if there's uncertainty about the model, if there's known modeling errors, known unknowns, then we can add that in and design this, compute the funnels that are robust for that entire family of models.
Are there degrees of freedom for the vortices, for the air?
No, because it didn't dominate our dynamics, and because our actuators aren't fast enough to keep up with it. But I'd love to do that. Yeah. Okay, so it's a very model-based approach, and this is a change from my initial line of thinking. I initially thought it'd be hard to model walking, and I was doing a lot of learning stuff, but now I believe in model-based stuff because the tools are just that much stronger. Ian's going to give a system identification tutorial today. There's a poster on system identification, which I put on Saturday so that it would sort of correspond with the tutorial. So SysID is actually working pretty well in these complicated systems. We're working hard with Sasha Magretsky to do on a new form of convex optimization-based identification. But there's good tools, I think, around and coming online for doing system identification. And we can still potentially do learning to accommodate for errors, differences between the actual model and the the model-based control. Okay, so, but what this means to me, I think, is that we've got these algorithms now which allow us to build systems which really exploit the nonlinear dynamics, even when they have complicated saturations and things like that, by these efficient algorithms for local trajectory planning and global feedback design, despite limited control authority, with a rigorous combination of local controllers.
Russ?
Yeah, sure.
So you have a discontinuous switch between control laws throughout your trajectory, for example, with walking, right? How many switches do you have, for example, a compass gate?
It's a continuous manifold of smoothly varying gain across the trajectory, yeah? And then at impact, there's a discontinuous switch, and it's continuous.
So when you transition from one funnel to another in the continuous trajectory, you don't have a discontinuity.
Okay, so in the case of planning the nominal limit cycle, absolutely, we make it a smooth connection to the next funnel, and the Riccati solution is backed up all the way to the goal effectively through. So there's no jump there. Okay. But for real-time planning, when we start throwing the funnels around on terrain we haven't seen before, then we're going to be sticking funnels together that weren't initially designed to be stuck together, and we'll have some jumps. But I think it should be robust for that.
Steady-state walking should be okay.
The jumps are less severe in this. I mean, you don't worry about chattering and switching because once you stay in a funnel, you live in the funnel. You don't tend to bounce the way we've designed it. There's not a total ordering the way Al liked to do it, but once you stay in the funnel, you live in the funnel and you don't chatter. Okay, so I think verification plus motion planning can enable rigorous and practical feedback design for non-convex problems in robotics. Legged locomotion, we're trying it in manipulation, we're trying it for other systems as well. And I think the real thing about these funnels, for me, apart from proving stability, is that it allows you to build sparse trajectory libraries. So we can achieve performance at the limits with strong theoretical guarantees. And now, so Andy, after the tutorial yesterday, said, compared to 5 years ago, I think a lot more people around here are pretty optimization savvy. There's just the number of people here that use optimization tools regularly seems to be going up, okay? So let's hope that maybe in 5 years, as we're talking less about limit cycles and more about walking in general and walking on terrain and stuff, and maybe we could say the same thing. Maybe planning's next, I don't know. Maybe that's optimistic. Hopefully you're all using RRTs, I guess, in 5 years. Okay, so just a teaser at the end here, but Rick's trying to do this perching with flapping wings now. We just started getting this to work, and we've been building robotic birds. But lots of fun things you can try to do with this sort of control. Okay, thanks a lot. Can I take your question?
Time for some questions? Go ahead.
Question about SumsofSquares.
Yeah.
The line-based approach usually sensitive to dimensional system.
Good.
So you have 5 states and it doesn't work.
Could you repeat the question?
Sorry, good. So the question is, how well does the SumsofSquares scale to higher dimensions? It's the absolute it's the most sensitive to dimensions of all the parts of the algorithm, no question. So we've done 6 degree of freedom satellites, so 12 states with quadratic Lyapunov functions. Ufuk Tapku says he can do 14 dimensions with quadratic Lyapunov functions. But that's probably the limit where we're at. We're probably 10 to 14 sort of before it really starts choking. So the claim...
We tested that it's up to 20.
You got up to 20, good, so I'll cite you from now on. So 20 sounds better. But it's not going to be 100, I think, anytime soon.
There is plenty of other algorithms for solving LQR similar type programming. tasks.
I'd love to talk about it.
600 or 100.
Can you say,
So-
can you repeat what he's saying?
He says that there's other tools available. I'm not sure I'm not sure we're talking about exactly the same thing. He says, so we're trying to do, so for the linear system analysis, I completely agree, you can get up arbitrarily high dimensions. I haven't seen yet other tools that can do the nonlinear analysis in high dimensions, but if you know one, then I'm happy to hear it.
What's the scaling? Follow up. What's the scaling? Oh, what? Yeah.
Ian or Mark could tell me, but it's polynomial in the number of variables that you get as a function of your parameters are roughly are polynomial in the number of dimensions, and then the complexity of the semi-definite program, I believe, is also polynomial in the number of parameters, but the coefficients are probably big. Yeah, but it's polynomial. Yeah.
You mentioned that the reachability guided sampling is ideal to quickly explore a high-dimensional state space. This sounds ideal for the initial periods of online reinforcement learning, where you also need to randomly explore until you find the goal for the first time. Have you tried it for that purpose?
I think reinforcement learning is best suited to places where you don't have perfect models, or any models, let's say, or to catch the slop between the model you're using for model-based stuff and maybe the actual optimal solution for the real system is different than the one for your model because your model's a little bit wrong. And that's where we're putting reinforcement learning back in. It's hard to do reachability estimates if you don't have a model. And so, yeah, so instead we basically do all the model-based control, model-based design, and then we allow the reinforcement learning to optimize within the class of verified policies. So we say, okay, this funnel is stable no matter if the feedback gains are in this range, and we allow a reinforcement learning system to move inside that regime, or at least that's what we're trying to do. And that's how I see them coming back together. Yeah?
If you just take the case of the compass gate, and you just put on your linear controller on the limit cycle, you have some basin of attraction, and then you do your whole routine, and you have a bigger basin of attraction. Do you have any way of, with a picture or a number or anything of describing
What's the difference?
how much bigger do you get than just the linear controller on the limit cycle?
It depends on the saturations. I mean, I think that's what really dominates, and I think that's the one that's hard to, and the foot scuffing and the hard constraints, the foot slipping conditions and things like that. So it's going to depend. The answer will totally depend. I could come up with a system that would be very impressive,
What would that be like?
something that was very torque limited, for instance, or had a low.
Limited, it would have like a fractal-like basin of attraction, or would some sort of dense region that's attractive?
It would have trajectories, for instance, that took multiple steps to get back to the goal, and were verified with
white space in between.
No, it would fill these up, but the solutions are not quick returns to the goal. They would have to maybe take multiple steps to get back to the goal, for instance, and each of them would have a fairly narrow tube because of the severe torque constraints, but you'd still power up and fill the space. Right? And if you give me a robot with complete control authority, then the difference between me and just a local controller is not going to be great.
I guess, let me say the question a different way. Let's say you had ultimate perfect control of all kinds. What is the accessible basin of attraction compared to that which you access with the linear controller? So you say, okay,
that's what I tried to answer.
I know,
yeah.
but you say you could fill up the accessible basin.
Yeah.
But the accessible basin might have a weird spirally shape to it.
Yeah.
And so the question is which is not that maybe useful in real life because there's so much white. Even though you say it fills it up, it still could have lots of white space in between. So
it might, if it's a weird shape, it'll take lots of ellipses to fill it up.
So the question: what's the nature of the shape of the ultimate basin of attraction compared to the basin of attraction of the linear controller?
Yeah, and I think the only answer is it depends. I mean, I can give you one where, like with very severe torque limits, where the local controller's basin of attraction is going to be small, and so Anton made the point that if you cut the surfaces right, they could look fairly ellipsoidal, or at least convex, and if you cut them wrong, they're going to look really strange. And how much bigger is the one with better control just depends on the torque limits, depends on the nonlinear constraints, right?
Well, I think
we're missing something.
Well, I don't know. If you're looking at the reachable and observable set in a nonlinear system without impacts, didn't Eduardo Sontag prove about 20 years ago that the set of trajectories along which the linearized system is controllable and observable will be dense?
I don't know.
So I think there
Sounds
are
good, though.
answers. I
Yeah,
think
reverse
people,
theorem like that, yeah. I know what
it's
you're talking
just
about.
like 20 years
Yeah, it
ago.
was a long
Most of us
time.
haven't thought about that. And he had a control design method which was involving patching linear controllers on that.
Yeah.
So if you go back and
Yeah.
look at that paper, it probably has the answer to Andy's question.
Yeah, okay, cool.
The answer is you're not going to get a lot.
Emo, you're about to talk, that's cheating. Anyone else have questions?
So my question is actually kind of more philosophical, surprisingly, because I mean I like all the theory. I like all the theory you're doing here, and I think it's a great approach. But there's got to be some sort of glass ceiling here, right? Because you kind of presented a universal hammer, right? Where you can say, give me any system, and I'll just do my funnels on it, and I'll do my trees, and I'll do some SOS stuff, and I'll give you a bunch of controllers that switch around. So where do you see this glass ceiling being, especially in terms of like complicated bipedal systems, right? So like, we're talking about getting up to what, at least 12 degrees of freedom at a minimum, and we want to do complex stuff, and we have all these really complicated constraining ground forces you'd have to check, and a million other things. So
Awesome. No, so I love it. So and then the ironic thing is in the other meetings, I'm the guy that says the dynamics matter and right? So, but, so everything matters, right? So if you do your mechanical design better, you're going to get bigger funnels, right? This is, let's just live in my world for a second. So everything's about making the funnels bigger, I guess, right? And the efficiency of the algorithm is going to depend, the coordinate choices you make, the parameterization using Amberish's model might mean you get really big funnels, or if it's not the right model, then maybe you get really small funnels. And the efficiency of the algorithm and where the glass ceiling is will depend on insights about walking and stuff like that. It's just I like universal hammers more. I guess that's just my style, right? So I'd rather do the think about that side of the problems. Yeah. So
Okay,
awesome.
let's hear it for universal hammer.